Hi, I'm Omar Polanco.
I'm Minauro.
And I'm Axel Pérez.
And we are Team Simic.
The challenge we faced was giving the puzzlebot the ability to navigate a track without human intervention. To achieve this, we focused on four key elements: traffic sign detection, traffic light detection, the line follower, and decision making.
Both traffic sign and street light detection were achieved with a neural network, using a YOLO BS8 model as the base and a custom dataset created and labeled with the collective effort of our professor Dr. Aceves and the rest of the class's teams. This dataset had a larger focus on turn signs and streetlights, as they were the trickiest ones to detect due to their physical similarities. Performance obtained by this final trained network had an average assertion rate of 90%, as seen here on the normalized confusion matrix, and observing precision recall curve, we can observe that the streetlights and the turn signs were both consistently and accurately detected, with an overall MAP50 score of 0.923 and a precision confidence rate of 0.952, ensuring accurate and reliable detection.
Line detection and zebra crossing detection were achieved by defining a region of interest, a ROI, on the lower third of the image and applying several filters to it. The first one was a Gaussian filter that smooths out the image to reduce the risk of false positives. Then brightness and contrast were adjusted to avoid big reflections in the detected lines. Finally, the offset threshold detector is used to create an inverted binary image in which a contour finding algorithm calculates the distance between the nearest area centroid and the center of the ROI. This distance is then taken as a positive or a negative error and published for the controller to act on it. Additionally, whenever 4 or more centroids are found in the image, the resulting state changes from a detected line to a detected zebra crossing. Finally, our efforts resulted in an expected performance. While some tuning was needed, especially in the parameters for the ROI, performance was satisfactory.
Taking the error value generated by the line detector as input, we designed a fuzzy logic controller that controls the twist of the puzzlebot. To create a control law that satisfied this requirement, we established several membership functions across all variable spaces. This was done to get a nonlinear response to the error and reduce the problems generated by a linear controller, such as instability and steady-state error. With all the components up and running, the final step for the robot to achieve complete autonomy is a state machine that takes the information generated by the computer vision node and the YOLO neural network to determine the actions the puzzlebot must take to comply with traffic laws. The design of this state machine became more and more complex as we took into account more cases that we observed during testing, giving us as a result a robust system that can navigate the track fully autonomously.
Once all of our nodes were completed and after rigorous experimentation, we decided that our best shot was to run the line and zebra detection algorithm, the state machine, and the controller directly on the jetson, to avoid latency interruptions. However, the neural network resulted impossible to run due to the high load of processing and RAM consumption.
After extensive testing of the complete system taking as a qualitative variable the number of times we had to intervene to prevent the robot from exiting the track, and the number of times the robot committed a traffic infraction, we determined that a robot had an overall reliability of 86%, out of 50 cycles that were run continuously and only interrupted when a catastrophic error occurs. We observed that the most common error was the mislabeling of the turn signs due to sharp angles of observation. The second most common error was a loss of the guiding line due to excessive reflections on the tape. In spite of this, we determined that the system is robust enough to perform its tasks autonomously for up to 10 cycles or 15 minutes, which is the longest uninterrupted running time repeatedly observed during this testing.